Are you confused by your sines and coses? Do you not know whether you're perpendicular or parallel? Well, this video is for you. I think the whole angles thing and the sine and the cos thing can be confusing, particularly when you get to slopes like this. So here's an alternative approach where we just use cos all of the time. Okay, so I'm going to look at this example here, and we're going to look at a couple of examples from the textbook. So firstly, a reminder that when we solve these sorts of problems, we resolve parallel with the plane and perpendicular to the plane. And those sort of signs are, understood, so you don't need to explain any more than that when you're doing your working. So this problem is quite straightforward, because when I resolve parallel to the plane, so I'm going to turn it this way, the reaction force isn't involved, so I've got one force pulling, this is something which is, I should have explained that. So it's a sledge. I think this is going up a snowy slope, so no friction, it's smooth. The sledge has a weight of 100 newtons. It's being, and two boys are fighting over it. That's the context of the problem. We've got one boy pulling up the slope with 70 newtons, another boy pulling down the slope, and it is staying still. So the question is, how hard is the boy pulling? Right, so if we resolve parallel to the slope, we've got the boy pulling up, and there are two forces pulling down. You've got this force, which we're trying to calculate, and we've got the component of this force. So let's work out the angle of that force to the angle that we're working at. So we're resolving parallel to the slope, so let's work out the angle of that force to that slope, okay? And hopefully you can see that if this is 35 degrees and this is a right angle triangle, then this angle here will be 90 minus 35, so that's 55 degrees, okay? So that means that the component of that force is 100 newtons times the cos of 55. So I always say use cos when you know the angle. Well, I'm just in this video going to work out every angle that I need. I'm not going to use sine at all. Okay, so resolving parallel with the slope. Up the slope, I've got 70 newtons. Down the slope, I've got F, and I've got 100 cos 55. And it's in equilibrium, so that equals 0. And so that allows me to work out the size of F. So I've got, going to add F to both sides. So I've got 70 minus 100 cos 55. That gives me the value of F. Just reaching for my calculator. So I've got 70 minus 100 cos. I've just realised I'm in degrees, so shift set up. So I'm in radians, I need to be in degrees. There we go. So 55. So that gives me the size of the force that the boy is pulling down. So that's 12.6 newtons. 12.6 newtons. Now actually we don't need to resolve perpendicular to the slope to work out F, but if we want to work out the size of this force, then we do. So let's now turn it again. So now we're working in this direction here. So the 70 newtons and the force F are at right angles to that, so they'll have no effect. So the only force I've got is the reaction force pushing up, and then the component of this force pulling down. So now I'm going to work out that angle there, and this is a right angle, so this angle will be the same as that angle. So if you know the angle, you use cos, and I'm only going to use cos today. So I've got going up R, coming down 100 cos 35, and that equals 0 because they're in equilibrium. So R equals 100 cos 35. So R is equal to 81.9 newtons. So I'm only using cos because I'm working out the actual angle between the force and the direction I'm resolving in. So when I was resolving parallel to the plane, I worked out the force, the angle between the force and the plane, and when I was perpendicular, I worked out the angle between the force and that meant I could just use cos. So this was one of the questions I suggested you tried in the second video, and if you're in the paper version, which hopefully you all are now, you've all got your copy. Well, if you're watching this Tuesday morning, you won't all have got your copy, but anyway, by the end of Tuesday, you will have got your copy. It's page 116, question 7. It was question 6 in the online version. So we've got here a 5 kilogram, I forget what the context was, it just says a 5 kilogram mass on a smooth plane, no friction, and it's being held in equilibrium by a string. So we've got to work out the tension in the string, which is pulling it up, and we've got to work out the reaction force from the plane pushing up on the mass. And obviously if it has a mass of 5 kilograms, it weighs 5 times 9.8 newtons. So I'm going to do the same thing as we've been doing. I'm going to resolve parallel to the plane firstly. So let's have a look at the forces if I resolve parallel to the plane. I've got the reaction force, which is at right angle, so has no effect. I've got this force here pulling it up, and the angle between that force and the plane is 30. And I've got this force pulling it down, and the angle there is going to be 80. I deliberately sort of drew this diagram a bit big, so it's obviously clearly not to scale. So I've worked out in both cases the angle between the force and the direction that I'm resolving in, so I know I can use cos. So I've got up is t cos 30, and down is 5g cos 80, and they're in equilibrium, so that equals 0. So t cos 30 equals 5g cos 80. There's nothing wrong with writing that straight away. So saying that one take the other equals 0 is the same as saying this equals this. Force up equals force down. If you prefer that, then that's okay. I've just noticed my grubby fingers. Sorry, bit of bike maintenance. I apologise. So yes, I can work out the value of the tension by just doing that sum. And here we go. So I've got, sorry, I've got, this looks funny because I've got the brightness turned up because it's evening. So it's 5 times 9.8 times the cos of 80, and that's over the cos of 30. So that's 9.82. 9.83, sorry, 9.83 newtons. That's the tension. Okay, so I'm now going to resolve perpendicular to the plane at right angles. I'm going to change colour for that. So if I'm resolving in this direction, then the forces are still all in effect. I've got nothing acting at right angles. So R is going straight up. The tension will also go straight up, and the angle that time is 60. And this force is pulling it down, and the angle, remember I'm working in this direction, I'm working perpendicular to the plane, so the angle there will be 10, because that angle there is a right angle. So, because I've worked out the angle between the force and the direction I'm resolving, I can just use cos. So I'm going to do it here. So resolving at right angles, I've got 3 forces involved. So I've got R going up, I've got t cos 60. Remember, this is the angle I'm resolving in. So that's t cos 60. And coming down, I've got 5g cos 10. And it's in equilibrium, so that equals 0. And you can then go on and work out R. I've just worked out t down here, stored the exact value. So r is going to be equal to 5g cos 10, take away t cos 60, using the exact value of that one. Let's look at one more question from the textbook. They use a similar notation in this textbook to the one we use in class. So this question's got to be good because it's exam problem solving. I actually don't know what M stands for, but there we go. It must be good because it's got all three there. So we're going to have a go at question 14. So here you've got a solar panel fixed to a roof. The roof is smooth, so no friction involved. And the force of the fixings is modelled as a force pushing it like that. Okay, so have a go at question 14. So that's on page 117. Question 14 on page 117. And pause the video at this point. So it's 117, question 14. Go away and have a go at that one. Pause the video at this point, and I'll come back in a second with a solution. Okay, so a lot going on here. So let's resolve parallel to the slope firstly. So that's this direction here. Let's turn it. So I've got R has no effect. I've got this force at an angle of 39 degrees to the plane, pushing it up effectively, and this force at an angle of 51 degrees to the plane, pulling it down. So up minus down equals 0 because it's in equilibrium. So that allows me to get 159 as my value of F, although I've stored the exact value, and that's because when I come to resolve perpendicular to the slope, I've got three forces. I've got the reaction force. This force at an angle of 51 is pushing it down, as is this force at an angle of 39. So both that and that have a downwards effect, which is counteracted by the reaction force. So I've got R minus F cos 51, take away 20g cos 39, 51, 39 equals 0. So R is equal to those two added together, and I'm using my value of F from before, and that gives me my answer. So if you're a physicist and you're used to doing the whole sine cos thing, cos when you know the angle, sine when you don't, then you can ignore this video. But if it was confusing you in the first couple of videos, this is certainly the way I work. I like to always know the angle and always use cos. So there we go. Hope that was helpful, and stand by for the next video. Although I will say that this is as far as I'm going to take it in terms of the mock. So that question 14, was an exam-like question, and although I haven't written the statistics and mechanics mock yet, I could well imagine that sort of question being the one that would turn up. We haven't covered friction yet, and there's a couple of other sort of variations on the theme, but I think that's pretty much the sort of level I will get to. I will carry the videos on though, because I want to get through as much of this as possible. Take care.